Only a few miles from the glamour of France's famed Riviera lies a little-known French national laboratory in large part used to conduct material analysis for next-generation semiconductors. But a team at the Valbonne lab, the CNRS-CRHEA, Research Center on Hetero-Epitaxy and its applications, is now analyzing 100 milligrams of tiny grains from NASA's OSIRIS-REx sample return mission to the asteroid Bennu. In fact, the Valbonne sample contains some surprises which will be announced by NASA as early as next week. Guy Libourel, a cosmochemist at the Observatoire de la Cote D'Azur in Nice and a OSIRIS-REx co-principal investigator, told me here. This object is very pristine because since it formed, it didn't evolve, didn't transform, he says. The sample, safely encased in nitrogen since its retrieval by OSIRIS-REx dates back to the earliest beginnings of our solar system's protosolar nebula, some 4.567 billion years ago. The French team has used a technique known as Hetero-Epitaxy to analyze various crystalline substrates to identify its mineralogy. Among other things, thus far they've identified iron oxide, lot of sulfides, the elements of manganese and magnesium, as well as silicate serpentines that point to the fact that Bennu was once rife with water. Some of the mineral fragments inside Bennu could be older than the solar system itself, says NASA. These microscopic grains of dust could be the same ones that spewed from dying stars and eventually coalesced to make the Sun and its planets nearly 4.6 billion years ago, notes NASA. What makes the French lab in Valbonne unique is that it is using a newly improvised method of cathodoluminescence. That's a process by which beams of electrons inside a scanning electron microscope strike luminescent materials and generate either an image or a spectrum. Marc Portail, a French CNRS research engineer, told me at the lab. Much of the Bennu sample material consists of silicate crystals capable of emitting light when bombarded with a high incidence of electron beams. By analyzing the luminescence from both the images and the spectra as the beams strike the sample, researchers learn details about the crystalline distribution of the sample's minerals. In short, the scanning electron microscope allows us to have a very detailed map of these tiny grains to detail the mineralogy, says Libourel. Meteorites that survive the violent, fiery descent to our planet's surface get contaminated when they land in the dirt, sand, or snow, says NASA. Some even get hammered by the elements, like rain and snow, for hundreds or thousands of years. Such events change the chemistry of meteorites, obscuring their ancient records, NASA notes. But the samples inside the spacecraft that landed in the Utah desert this past September were wholly protected from the ravages of crossing Earth's atmosphere from the get-go.